Okay, gentlemen, I want you to turn off your mobiles and keep your mobiles in the pockets and hope for the internet to continue working. Look at the screen for the full name. I have, by the way, uploaded assignment number 2 and assignment number 3. And because I was late in uploading number 2, so the date I gave you 2 days to upload. By 2 days is Thursday, right? Thursday. It's back. Plus, the interval is decreasing, so it's getting better. Muhammad Mustafa. Muhammad Ahmad. Hussein. Yes. Saud. Abdullah. Saud Abdulaziz. Salman Fahad. Muhammad Ahmad. Yes. Salman Abdullah. Faisal Fahad. Muhammad Abdullah. Fahad Khalid. Yeah. Abdurrahman Adil. Yes. Muhammad Suleiman. Yes. Muhammad Ahmad. Yes. Hamid Hani. Yes. Muhammad Haytham. Adi Farooq. Ibrahim Hussein. Yes. Yusuf Muhammad. Yes. Hussein Abdul. Yes. Hassan Ahmad. Yes. Abdul Hadi. Yes. Ahmad. Yes. Jawad. Yes. Ahmad yes. Mirza. Abdul Aziz. Yes. Ahmad Assam. Yes. Mishal. Yes. Saad. Fahad. Yes. Abdul Aziz. Yes. Okay, we were up to the point where we proved some properties of the OLS estimators. Today we'll try to wind up the chapter, and today you expect 2 more assignments. Number 4 and number 5. 5 will be a long-term assignment. The deadline will be up to major 1. Whenever is the major 1 day before the major 1, there will be the deadline for 5. 4, you need to do it quickly. Okay, I think by the end of the last class, we were discussing about coefficient of determination, if I'm not wrong, is it? So let us start the discussion about coefficient of determination. Now, once you fit the regression, you do everything. The next target is to see how good is your regression. So these type of measures, although there is a complete chapter on these type of measures to see the goodness of your regression, yes? Yeah, wait, just let me confirm if the recording is on. Yes. Now we're talking about this model. We're talking about this model, and in this model, if you look at the right side of the model, there are 2 components basically. One of the components is called your regression, and one of the components is called your error. Right? Now, the whole variation in y, the total variation in y, it is denoted by SYY, which is basically the variance in y, and you ignore the n-1 term. This is also called in regression terminology, and in your previous course, you also called it SST. Sum of squares of total. This is basically a measure of how much is the total variation in y. And this is nothing but its summation of yi minus y bar whole square. The same thing we call SYY. This tells you how much is the variation in y. As simple as this. Now, if you look at the model, the total variation in y, some of it is because of the regression and some of it is not because of the regression. Some of it was explained by your regression, which is this first part of the regression, and some of it was not explained by your regression. You called it error. This part of the variation was not explained by your regression. For example, if y is your expenditure, x is your income, some of the expenditures are determined by the income, but not all of them. You can give an idea about the expenditures of a person if I tell you the income, but it will be plus or minus something. So some part of the expenditure is going to be explained by the regression, by the predictor or predictors, but some part will never be explained. This unexplained part is called the error. And in regression terminology, this total variation in y is basically sum of two variations. One that is explained, this explained variation, you call it SSR, the sum of squares due to regression. And this unexplained variation, you call it SSE. We already know the formula of this SSE. What is it? This is summation EI square, basically. SSE, sum of squares of residuals, errors. So if I ask you to find this SSR, can you find it? Simple. SST minus SSE. And for simple linear regression, there is a direct formula for this SSR. This is beta 1 hat times SXY. I'll see if we need to derive this one, or I'll do this derivation directly for the multiple regression, because this whole chapter becomes a special case of multiple regression. In multiple, we'll assume we have k predictors. So if k is 1, you come back to this. Now, my question is, what do you want ideally from your regression? You want the explained variation to be maximized or unexplained variation to be maximized? You want the explained to be maximized, right? How much maximized? You want SSR to be maximized or SSE to be maximized? These are the two components. Which one do you want to be maximized? You want SSR to be maximized. How much maximized? You want it to be 7,400? As much as possible. With reference to what? What's the reference point? What's the maximum value it can attain? It can maximum go up to SST. That's the total. If you look at the three names, they are sum of squares, right? Can squares be negative? They will not be negative. So the sum of those two will be equal to this, which means that those two cannot exceed the left side. They will always be smaller, and their sum will be equal to SST. Now the maximum value SSR can attain is equal to SST. In that case, SSE will be 0, right? And when will SSE be 0? When all the points are on the line, exactly on the line. And it's a mathematical relationship, not a statistical relationship. So you want this SSR to be maximized, but you want it to be maximized relative to what? Relative to the total possible variation in Y. So you want this thing to be maximized. You want to see this SSR relative to SST. What is the domain or the possible values of this thing? Between 0 and 1. Let's talk about the two extremes. When it will be 0. When SSR is 0 and that second component is dominating, in that case, the regression will be good or bad? Very bad. And about the other extreme, SSR is dominating. In that case, the regression will be perfect, very good. So this measure, this ratio is called coefficient of determination. It is denoted by R square. Again? Is it possible to get 1?
for the preparation by.
In real studies, no. Exactly one, no. It will only be possible if it is a mathematical relationship, like y equals 2x plus 5 plus nothing epsilon. Logically, it should not be. It should be less than 1. It can be close to 1, but it will never be 1. Now, we all know how do we interpret this R square. This R square is basically what it is, the SSR divided by SST. SST is the total variation and SSR is the variation that is explained by your regression. So if you take the ratio, this is the proportion of variation that is explained. The ratio is called what? If you talk in terms of probability terms, probability is what? N of event divided by the total, right? That's called the probability or the proportion. This is basically the probability. If you multiply it by 100, it becomes what? Percentage. So R squared tells you the percentage of variation in Y that is explained by the regression. I'm writing regression and I'm not writing X because later I will have more X's. So I'm writing a general word regression. But for this case, I should write only X. It's the amount of variation in Y that is explained by the predictor X. Later, I will have more predictors. And of course, we want this percentage to be maximized. Now, the question is, how much maximum? There is no answer to this thing. Is 90% good? 99% good? Is 80% good? We don't know. We don't know. This depends upon the sensitivity of the variables. Sometimes the variable are so sensitive, even 95% is not good. 99% is not good. And sometimes the variables are not sensitive, 70% is even okay. I'll give you an example. Let's say if I plant 100 flower plants outside here and give them water every day. And after 100 days, one of the plants, it dies. 99, they remain. So is this result good enough for you? 99 are still alive. Is it good enough for you? It's a very significant result, very good result. Whatever you are using, you should continue to use the same methodology. It's saving plants, right? What if instead of plants, there are humans? One human died. Now, this is significant. Although it is 1 out of 100, it is very significant. Wherever the variable, the nature of the variable is sensitive, even 99 is not enough. So there is no absolute criteria for a high value of R square. No absolute criteria. It all depends upon the nature of the Y variable. If it is very, very sensitive, even 99% is not enough. If it is not very sensitive, sometimes even 70% is enough. That's all you can achieve. So the interpretation of R square you can interpret, but you cannot control it. Whatever it is, you just need to interpret. Now, there is one topic that is left in this chapter. Yes.
Is it possible to have some sample questions on this chapter?
Remind me after the class. I have been mentioning this discussion again and again in almost every topic. I want you to go and read section 2.9. This is just theory, nothing mathematical, nothing statistical. It's just some considerations about the regression. It talks about what should be the domain of the variable, what should be an outlier, although there is a complete chapter on outliers. What are the outliers in terms of regression? There is a whole chapter on it. We'll cover all these things one by one in the later chapters. But just to introduce yourself to these concepts, read this 2.9. Regression through origin is the one topic that is left. Let me leave that one to the end and I will discuss this 2.11. Now, since day one, we have been assuming what? The x's are fixed, right? And we only talk about the distribution of y for a given x. There is a complete population of y for a given x. We always say given x. We always assume that x's are given, fixed, right? What if they are not fixed? If they are not fixed, what will happen? I'll not go theoretical on this one. If they are not fixed, you will not be talking about f of y for a given x. You will not be talking about f of x for y for a given x. You will be talking about f of y and x, the joint distribution. Which we talk in which course? We talk in 301. We talk in 212, 211, sorry. The joint distributions is chapter 5 of 211. We talk in 211, but the good news is we'll not talk about this in this course. Now, when we have the joint distribution, the ordinary least square method doesn't work because we don't have a compact objective function like we have for one variable. We don't have it. In that case, there is another method that works for the joint distribution, and that method is called maximum likelihood estimation. There is ordinary least square estimation and there is maximum likelihood estimation. And the good news is, after going through all this maximum likelihood mathematical derivation, you end up with these formulas. You end up with these formulas. If someone is interested, let me know. I'll give you the proof. But we close this topic here. And what do we learn from this one? Even if x is not random, even if x is random, what are the formulas that we are going to use? The same. So all the theory that we established first by assuming that x's are fixed, that can also be applied when x's are not fixed. Now, when x's are not fixed, there is another concept other than regression that we apply. That concept is called correlation. This is what we will talk about. What is correlation? Again, this is the same chapter 2. See, when I start, you will get to know I started. You will feel it. You will feel something new. It will be. It will be. Inshallah. The concept of regression, basically in regression, you specify that this variable is the predictor variable and this variable is the response variable, right? So there is a one directional relationship. The second direction may be true, may not be true. You are not interested. You are not interested. You are saying that the time of filling the machine is dependent upon the volume of the machine. The other way is not true. The other way, you are not interested. So it's a one directional relationship. Sometimes you are interested in a descriptive statistics called a relationship between the two variables, regardless which one is affecting which one or which one is not affecting. You just want to see how they are related. If one is moving in one direction, where is the other moving? So to study that concept, we have a measure called correlation. This correlation is what it measures. We have talked about this thing already. It measures the strength of linear association between the two variables. Again, correlation coming out to be 0 doesn't mean they are not associated. They are not linearly associated. So if I have a data something like this on x and y, I can guarantee you if you find the correlation of this data, it will come out to be 0. It will be 0. But they are very strongly related, very strongly related. But the correlation, of course, will be 0. So correlation, it measures the strength of linear association. It is denoted by R. It is SXY over SXX times SYY square root. Let me go a little bit into the formulation of this this SXY over square root of SXX times SYY. Yes.
Correlation is one-sided relationship, or
It's no-sided. You don't determine the sides.
just see how they're.
You just see how they are related.
Statistics where we can find the relationship which is not linear,
Not?
linear.
not linear.
Yes, we have. We'll talk about curvilinear things. I think we had this discussion before, but let us repeat. SXY, I wrote the formula at the top. Focus on this formula. The formula is basically two components. One is x minus x bar. Second is y minus y bar. And for all the points, we will sum this thing. We will sum the product. Now, tell me if your data is plotted like this. Pick any point from here. Let's say pick this point. For this point, what is x minus x bar? Assuming that we are talking about the planes, I brought them to standardized form, and this is x bar y bar. This middle point is x bar y bar. I standardized the data with respect to the means. Now, in this case, for this point, x minus x bar will be what? Positive. What about y minus y bar? Positive. What about the product? Where is the formula? What about the product of these two? Positive. So one positive, and product will also be positive. Right?
Yes.
So your SXY, look at most of the points. Will this be the same pattern for most of the points?
Yes.
Maybe there are some points here, maybe 1 or 2 points here in the second and fourth quadrant, maybe. For those, this will be negative, right? But for most of the points, the product will be positive. And ultimately, when you take the sum, the positives will dominate over the negatives, true? And the final answer of SXY will be positive. Similarly, if the relationship is something like this, if the data are something like this, most of them will be negative, and the ultimate answer of SXY will be. Now, SXY is a good enough measure to identify the strength of linear relationship between the two variables. SXY does tell you. The answer of SXY is good enough to tell you if the linear relationship is positive or negative. Why do we divide it by this factor? The answer is the domain of SXY is from minus infinity to plus infinity. You standardize it between nice two limits to make it relative. Make it relative to -1 and +1. To bring it back to the scale of -1 and +1, you divide it by this thing, and it comes back to the scale. And now you have a very nice scale between -1 and +1. Something close to -1 means what? A very strong linear negative relationship. Something close to +1 is what? Strong linear positive relationship. Something close to 0 is what? Weak or no linear relationship. Yes. If you divide SXY by n minus 1, it becomes the covariance. No difference. No difference. What is the difference between sum of x and x bar? Sum of x is the total and x bar is per unit, right? Per unit. So if you divide by the number, it becomes the variation per unit. Sxy is the total variation. If you divide it by n-1, it will be per unit variation. Now, this is descriptive, right? R is only describing the strength of linear relationship. What if you want to draw conclusions about? By the way, what is the unknown parameter that we are estimating? What is this R estimating? The population correlation coefficient, which is denoted by rho. Of course, on the two variables x and y, you have a limited data, but there exists a population of infinite many units. You cannot study all of them. The correlation between those all of imaginary units is rho. This is rho. You can't have all the units studied. So what you do is you take a sample and the sample correlation coefficient is called R, which is estimating rho. What if I want to do some testing about rho? Same hypothesis. I can be interested in rho equals 0, rho not equals 0, rho greater than equal to 0, rho less than 0, rho less than equal to 0, rho greater than 0. Same three types of hypothesis. And the test that is used to, to test this hypothesis is t-test. And this is the test statistic with n-2 degrees of freedom. And the same rejection regions that we discussed for beta 1, same rejection region. For two-sided, the rejection region will be two-sided. For one-sided, the rejection region will be one-sided depending upon the direction of H1. Exactly the same. Let me quickly show you. If you do find time, look at this joint distribution, and by the end, you will go through whole of this, and here are the estimates. The same that we get from OLS, the same from MLE. Okay, for testing rho equals 0 against not equals 0, this is the test statistic, and it follows a t-distribution with n-2 degrees of freedom. Here is the rejection region. You reject if t not absolute is more than the critical value. Now, this t-statistic can only be used if you are testing rho equals 0. If you want to test something else, rho equals 0.5, rho equals 0.9, anything other than 0, then this statistic does not become t. You cannot apply this. This is only applied when your population correlation is 0. Only then this statistic follows a t-distribution. Otherwise, it doesn't. In that case, what do? We have an approximated z statistic. In that case, if you want to test anything other than 0, we have an approximation called z approximation. And this one is no, for anything, for anything. Okay, for that situation, we have an approximation which says tan hyperbolic of R, it's tan hyperbolic inverse of R. This follows a normal distribution with the mean tangent hyperbolic inverse of rho, and the variance is square root of n minus 1 over n minus 3. This is a very useful approximation. This I'll give you in the formula sheet, but you need to know how to use it. To use this approximation, what you need to do is here is the complete guide. Suppose you want to test that rho equals 0.5. Let us say an imaginary number 0.5 against H1. Against H1, rho is not equal to, let us say, 0.5. What you will do is you will calculate a z statistic. This will be tangent hyperbolic inverse of your R, whatever comes from the data R, the value of correlation, minus tangent hyperbolic inverse of the value you are testing, 0.5, divided by square root of variance, right? Hyperbolic inverse. You don't know it? Math 101, Math 105, Math 105. You didn't do it? You forgot it? If you forgot it, you don't need to know don't need to go into the details, because the major exam will be on Microsoft Excel, and there is a direct command in Excel to find hyperbolic. I'll give you idea. You don't need to know. I'll show you. I'll show you. Let's say this is your X and this is your Y. Is it big enough? And let's say this is the data 2, 3, 5, 6, 8, 10. And here we have 15, 13, 10, 11, 8, 9. Let's say this is the data. For this one, I find the correlation. The command is CORREL. Here I have to give X's, comma, Y's. And the correlation is minus 0.89, right? A negative linear association between X and Y. This can be easily confirmed by the scatter plot. If I make a scatter plot, you will be able to see it. Is it clear? Up to this point, the descriptive measure. Let me start from 7. Look at the data. Clear up to describing the strength of linear association. Now let's say I want to test that rho is, let's say 0.9. I want to test the rho is 0.9. This is the hypothesis. So what I'll do is I'll take tangent hyperbolic inverse of R minus tangent hyperbolic inverse of 0.9 over the square root of 1 over n minus 2. So my z statistic will be let me try to recall. What is tangent hyperbolic? Here it is. A tangent hyperbolic. A tangent hyperbolic. This is the command. A tan hyperbolic. This is tangent hyperbolic inverse of this R minus tangent hyperbolic inverse of 0.9 whole divided by or whole multiplied by square root of what is n? 6. 6 minus 3 is 3. You get the point? Why am I multiplying? It's 1 over n minus 3, so it comes to the numerator. So the value comes out to be what? Minus 5 point something. And then you apply the same rejection region approach of standard normal or the same p-value approach. Again, n minus, n is 6. So 6 minus 3, the formula, the variance is n minus 3. Y minus 3, this is not exactly, by the way, this is not exactly normal. This is approximately normal. And through derivation, if you look at the distribution of this thing, it is proved through derivation that it is n minus 3 and not n minus 2, or not n minus 1. It is what it is. There is no reason for this one to be n minus 3 or n minus 4 or whatever. It's proved mathematically. It comes out to be like this. Now, once you have this one, and I got this one to be minus 5.02, I guess, is it? Minus 5.02, yes. Once I have it, I have the option to either go for a critical value approach or p-value approach. So if I want to go to critical value approach, I will reject H0 if the absolute value of my z is greater than z alpha by 2. Let me call it z1 minus alpha by 2. So let's say my alpha is 0.05. What is the value of z1 minus alpha by 2, the most popular value? 1.96. So I will reject H0 if this absolute is more than 1.96. Is it more than 1.96? It is. So I will reject H0 and I will call it to be not equal to 0.9. Did I put 0.9?
Yes.
Let me check. Yeah. But it's very close. I should have accepted. I put plus 0.9. I put plus 0.9. The intention was to test minus 0.9 because this is close to minus. What if I'm testing minus 0.9? Is this close to minus 0.9? What if I do that? Should I be accepting H0 or rejecting H0? I should be accepting because the sample value is very close to what I'm testing, right? So let me try. If I put minus 0.9, I get a z value of almost close to 0. That's the center of the z. Close to 0 immediately means you should be with H0 because this is obviously less than what? 1.96. So I should be accepting H0 in this case because minus 0.89 is far away from plus 0.9. That is why you are strongly rejecting H0 in the previous case. If you want to use the p-value approach, you can use the p-value approach, and here is the expression. The p-value is 2 times probability of z more than absolute value of z0. So if I want to use it in Excel, Excel will not give me more than probability. Excel will give me less than probability. I can take 1 minus to make it more than. So I'll go into z and I'll use the command. What is it? Norms test. What is the value of z? 0.07. Do you want cumulative area? True. But this command will give me the lower tail area, lower than 0.07. I need to convert it to upper tail. I make it 1 minus, and then I need to multiply it by 2. So I put a bracket over whole thing and I multiply it by 2. Again, because it's a two-sided H1, not equal to. If it is one-sided, you will not multiply by 2. 2, yes, because H1 is two-sided. True means, okay, wait. Anyone who knows why is it true? Basically, for normal distribution, this is your f of x, right? This is your, have you seen this before? 1 over square root of 2 pi e to the power minus 1 by 2 z square. This is standard normal distribution with sigma equals 1, mu equals 0, right? If I want the probability of z between less than, let's say probability of z less than 0, which is of course 0.5, is it? Do you all know that probability of z less than 0 is 0.5? The center of z is 0, so 1/2 is less and 1/2 is above. How do I find this probability if I want? I need to integrate from minus infinity to 0, this function. But Excel, it integrates itself and gives the answer 0.5. But the point here is that to find the probability, what do I need? I need to integrate, right? From minus infinity up to that point. If I want it probability less than 1, I will integrate from minus infinity to 1. If I want it less than, let's say, minus 1, I'll integrate from minus infinity to minus 1, right? Now, what is the meaning of this integration? Let's say this is the curve. And for standard normal distribution, this is the center. The lower limit is minus infinity, the upper limit is plus infinity. Now, what is the height of the curve here? 1 over square root of 2 pi e to the power minus 1 by 2 times 0, right? 1 over square root of 2 pi. And the curve is highest here. True? In any of the previous course, were you ever interested in the height of the curve? Never. You were always interested in the area below the curve. You were always interested in this integral, never interested in the height of the curve, right? Never. If you put false, it will give you the height of the curve. If you put true, it will integrate from minus infinity up to that point, and it will give you the area below that one. So to get the short answer is, to get the probability, you need to put true. To get the functional value, you need to put false. And to make it easier for you, we are never interested in functional value. So we never put false, right? But for those who are interested, false will give you the functional value of the PDF. The functional value of the PDF, or what we call the height of the curve. True will give you the lower tail area, the probability. Yes.
What does the functional value?
The functional value tells you that how probable is this value, because in continuous distribution, you say that probability of getting exactly 0 is 0, right?
Yes.
So how probable is to be in the surrounding of 0? First assignment of today. What you have to do is, this is a model. Which model is this? This is called no intercept model. You see intercept in this one? No. What you have to do is, in these 4 weeks, whatever we have done with the intercept model, you have to do it everything for no intercept model. That means you have to find beta 1 hat, derive. The objective function will obviously be summation epsilon I square minimize. Same OLS. So here the objective function summation epsilon I square will be yi minus only beta 1 xi. There will not be any beta naught. So you have to minimize that one, and you will get the corresponding beta 1, number 1. Then you need to identify the distribution of beta 1. Then you need to find the mean of beta 1 hat, the variance of beta 1 hat, design the t-test for the testing of beta 1, the expressions for SST, SSR, SSE. This is only one section. This is section 2.11. Yeah, I think this is it. I know. Did I choose to enter the CX? Yeah, I think this is it. Yeah, somewhere you will need the expression for MSE. You need to derive MSE also. Of course, yes. I will connect it with the real life. In real life, sometimes you are unable to interpret the intercept. For example, X is the investment, Y is the return, right? If I have no investment, what will be the return? No return, true? So if I fit a usual model on this one, my beta naught hat will come out to be a number other than 0. Can I interpret this that in case I don't invest anything, I will get a return this much? I cannot interpret. So in these examples, there is no meaning of the intercept. We should fit the non-intercept model here. We should force the line to pass through 0, 0. It should be, but it's not guaranteed. It's not guaranteed. Sometimes you have a limited data for which you get a positive beta naught. And this is not true. You should not get it. This is the one that I need it quickly.
No.
The one I don't need it quickly. Don't worry. I'll give you a website link here. Look. This is easier. Go to this website. Where is it? I think this one. Yeah. Go to this website. And on this website, you will find a number of data sets, with sections. Categorical data, we are not interested. We are interested in a section where we want the data for linear regression. You scroll down, you will see that section. Look here. The section is LR1A, only 1A. This is for linear regression, okay? You will see a number of data sets here. The data, the description, the data, description. Go find a data for yourself. Identify what is X, what is Y, and just run the regression and bring the results. Okay. Before the major, this is for before the major. Until major. Take your time. Yes, of course, on Excel. Just extract X and Y and try to understand what is X, what is Y. Understand the nature of the variables, how they are theoretically linked with each other. Try to write a few lines about we expect a relationship between X and Y. We expect positive or negative relationship, and this is what we get. The first thing we do in regression is to draw a scatter plot. We visualize the thing and then try to find B naught and B1 and do some testing and whatever you like from chapter 2. So implement all the knowledge of chapter 2 on one of the data files from here.
You make it also before the major because we need to study the material for the major in order to implement those.
Yes.
No problem. No problem. There are more coming. For me, no problem.
So we can.
And does any one of you have an exam of 11th of September, 6 o'clock?
11th. So
11th of October.
which is 302.
Which is Tuesday. Which is Tuesday.
Start 302.
Who's the instructor?
All of us.
Who's the instructor?
I
I will talk to Assam. Anyone else? What is the time of exam?
I did not choose.
I will talk to Assam. Don't worry. Don't worry about 302. Anything other than 302. Ask your instructor to write me an email that we have an exam. No 15. If you